Good morning, students. Welcome back to online classes of microprocessor and microcontroller. We have been discussing the second unit, and the second unit in which we have already discussed the assembly language program, structure of assembly language programs, and the assembler directives. And after that we have studied the one of the important integrated circuit, that is programmable peripheral interface we have discussed. In this video I am going to talk about the very important topic, that is memory and I/O devices interfacing with the 8086 microprocessor and 8085 microprocessor. In the last class we have discussed an integrated circuit which is going to make the synchronization of 8086 microprocessor with the input output devices that are keyboard, memory and output, and that integrated circuit is named as 8255 PPI, programmable peripheral interface. In this class I am going to talk about, by taking the memory, how this memory is going to be interfaced with the 8086 microprocessor. We know that 8086 microprocessor is having the 20-bit address bus. That means these 20-bit address lines will access the maximum of 1 megabyte of memory externally, and each location in the 8086 microprocessor is able to store the 16-bit of data, because the 8086 microprocessor is a 16-bit processor. Here, that 1 megabyte of memory, we know that 8086 microprocessor can be interfaced with a maximum of 1 megabyte of memory, because it has 20-bit address lines which can define the memory capacity of 1 megabyte. And in this video we are going to discuss how this 1 megabyte of memory can be interfaced with the 8086 microprocessor. How the 1 megabyte of memory can be interfaced with the 8086 microprocessor as 8085 microprocessor we are going to discuss in this video. The topic is memory and I/O interfacing with the 8086 microprocessor. Memory and I/O interfacing. I/O nothing but it is input output device. How the memory and how the input output devices can be interfaced with the 8086 microprocessor we are going to discuss now. Introduction: we know that microprocessor can read the data from the memory. Microprocessor can write the data into the memory. Not only accessing of data, microprocessor can fetch the instructions from the memory. And based on those instructions, that is nothing but a set of program, and it is going to serve one particular application. In performing specific applications, the microprocessor has to fetch the instructions from the memory, so that the microprocessor has to be interfaced with the memory, then only it can access the data from the memory and it can fetch the instructions from the memory. Need of memory in performing some specific application or in performing the applications, microprocessor has to read the data from the memory, or it has to write the data into the memory, and it has to fetch the instructions from the memory. And in order to do all these things, the processor has to be interfaced with the memory. Memory is also named as it is a storage device. It is a storage device. The capacity of a memory can be defined by the number of address lines it can be accessed. Based on the number of address lines in which the memory can be accessed, based on that one we can have the memory capacity of any storage device or the memory. In case of 8086 microprocessor, the 8086 microprocessor is having the 20-bit address lines. 20-bit address lines. 20-bit address lines. These 20-bit address lines can have the maximum capacity of 2 power of 20. 2 power of 20 means it is about 10,48,476 memory locations. This 2 power of 20 means 2 power of 20 address lines. 2 power of 20 address lines is nothing but 10,48,576 memory locations it can have. From 0 to 10,48,576 memory locations it can have. Each memory location can have the capability of having this, can have the capability of storing the 16-bit of data. Because this 8086 microprocessor is a 16-bit processor. So that 2 power of 20 is nothing but it is 10,48,576. That means if you approximate this one, that is about 1 megabyte of memory. 1 megabyte of memory. That means what? 1 mega is about 10 power of 6. Byte is nothing but 8 bits. 1 into 10 power of 6 into 8, you can go with that is about each location can capable of having the 8 bits such that you can have the value of that. That is almost 10,48,576 location can be having the memory, maximum memory of 1 megabyte. And this 1 megabyte memory is nothing but it is a semiconductor memory. It is a semiconductor memory. In this semiconductor memory, each location in the 10,48,576, each location can capable of storing the 16-bit of data. And here this memory can be RAM and ROM. RAM stands for random access memory, ROM stands for read-only memory. This semiconductor memory can be RAM and ROM. Then RAM is going to store the system software. That is whatever the software is required for the system to run the show, and that software will stored in the RAM. And that microprocessor is going to perform a specific function and it is going to perform a specific application. That application software will be stored in the ROM. ROM stands for read-only memory. Whenever the processor is going to serve that application, it is going to read that software. Software is nothing but it is a set of programs, is nothing but software. It is going to fetch that software such that it is going to finish that application, and so that whatever this application software is there to complete a specific application, and that will be stored in the read-only memory. ROM stands for read-only memory and it is a volatile memory. And RAM will store the system software. To run anything, the system need to go with some set of programs. That set of program nothing but it is a software. And before going to study how the 1 megabyte of memory can be interfaced with the 8086 microprocessor and 8085 microprocessor, we must understand the memory organization. The basic memory organization first we should know. If you are good at the basic memory organization, then you can apply the same knowledge to study or to understand the 1 megabyte of memory. After understanding the memory organization of 1 megabyte of memory, now we can study how to interface that 1 megabyte of memory with the 8086 microprocessor. So now I am going to explain about the basic memory organization of 8086 microprocessor. The now memory organization of 8086 microprocessor I am going to explain. So now here the semiconductor memory, that is nothing but it is a RAM or RAM, will consist of some registers. It has some array of register. Array of register means the collection of register, collection of similar registers are named as array of registers. That means if you go with the any memory in the semiconductor memory, that may be RAM or ROM, it consists of array of register. Register is nothing but it is a group of flip-flops. Group of flip-flop. Flip-flop is an element which can store either 0 or 1. So that here we are having a semiconductor memory which includes the RAM and ROM, and in the semiconductor memory we will have array of registers. Register is going to store the binary information, and each bit can be stored by making use of a flip-flop. This is about the introduction about the memory organization. Then the size of the memory, that may be RAM or ROM, can be described by making use of the formula, that is N by M. If you take any memory, that may be RAM or ROM, that can be described by making use of N by M. Size of the memory can be described by making use of N by M. We should not study this is N into M, it is N by M. N is nothing but it is the number of address lines of that memory, number of address lines. And whereas 2 power n is nothing but 2 power of n represents number of registers are there in the memory. And M is nothing but the size of each register. That means what? How capable that register is, how many bits that register is going to store the data. How many bits of data that register going to hold the data, that is nothing but M. Here you should remember the point is that the memory that may be RAM and ROM can be described. Size of the RAM and ROM can be defined by making use of the formula, that is N by M. N is nothing but number of address lines. N is nothing but number of address lines of the memory, and M is nothing but word size of the each register. Then the number of registers are nothing but 2 power of n. For example, I am having the two address lines for the memory, and so that two address lines it is having, so that how many registers that can access? 2 power of 2 means 4 address lines, 4 registers it can access based on the value of M, and that is going to store that many number of bits in that register. For example, M is 8 bits, that is 1 byte. M is equals to 8 bits, that means 1 byte. So that 2 power of 2 is equals to 4 registers are there. Each register address is 00, 01, 10 and 11, and each register is going to store the data of 1 byte. I hope I am clear that here semiconductor memory is nothing but it is an array of register, and this register is capable of storing the binary data, and that a register is composed with the flip-flop. Flip-flop is able to store the 1 bit of information, and the size of our capacity of that the memory can be described by N by M. N is equals to number of address lines, whereas 2 power of n is nothing but number of registers that can access in the memory, and M is nothing but the size of the register. And here semiconductor memory, and we can go with the semiconductor memory that may be RAM or ROM, will have the two types of pins. Why we are discussing memory organization? Because if you are good at the basics about the memory, and then we can apply the same knowledge to understand the 1 megabyte of memory, so that will be very easy to understand how the 8086 microprocessor can be interfaced with the 1 megabyte of memory. The memory capacity can be described by, the memory capacity can be decided by the number of address lines only, we must remember. The memory capacity can be defined by, can be decided by the number of address lines and the word size. That means number of address lines and the size of a register. And likewise, if you know those two things, we can obviously calculate the what is the maximum capacity of that memory. And in case of memory, that may be RAM and RAM. RAM stands for random access memory, RAM stands for read only memory, and we can have the two types of pins. RAM and RAM are available in the form of ICs that can have the two types of pins, and that pins are address or data pins. Address and data pins. First type of pins we can have in the RAM and RAM is address and data pin. Address is nothing but address pins are going to identify the one particular memory location, required memory location in the total memory space. That means what? Address lines will identify assign the unique addresses for each memory location. Address lines will assign the unique address for each memory location in the total memory space. Whereas data lines is nothing but they are going to define the size of the register, how many bits are going to stored in the register, that defines by the data pins. And the next one is about control pins. That means what? The operation of that memory device can be controlled. Operation of that memory device can be controlled by these pins, and these pins are named as control pins. What are the control pins we have? This is about chip select. Chip select means in order to make a function or in order to get the function from the memory device, that may be RAM and RAM, and it has to be selected. First that RAM has to be selected, and it is active low signal. CS bar. CS stands for chip select, and it is active low signal. Whenever it takes the 0, the chip will be selected for the required operation. Next one is output enable. Output enable. The chip is, once the chip is selected, if this is a random access memory means we can write the data and we can read the data. So that whenever we are reading the data, that will be the output operation. That means what? Whenever output enable, this is active low signal, whenever the output enable is 0, then it can fetch the instructions or it can read the data. And coming to the next one is read and write. When in case of random access memory, we can have the read and as well as write, because it can capable of read and write functions. And we can write the data into the RAM and we can read the data from the RAM, and this is read and write. If that is taking the active high signal, that is 1, so that it is going to give the read operation. That means the processor can read the data. If it is taking 0, then the processor is going to write some data into the memory. Next one is about VCC and ground. VCC is nothing but it is plus 5 volts, that is a required biasing voltage to on the device, and the ground, all the negative terminals will be grounded. So now we are going with the one particular example, that is about RAM I am taking. By making use of these two types of pins which are available for the semiconductor memory, I am going to describe the same by making use of the RAM. RAM stands for random access memory. RAM stands for random access memory, and here I am going to explain that. Here number of address lines, this is RAM, assume that RAM, and it can perform read operation and as well as the write operation. It can perform read operation and the write operation, so that it is having the n number of address lines. N number of address lines. Address lines are n, so that these are connected to a decoder. What is the function of decoder? What is the size of the decoder? If the inputs are n, then the number of output lines from the decoder will be 2 power of n. 2 power of n, that means what? Here we are giving the n number of address lines, so that it output of a decoder will be, it is a decoder to which we are giving the n number of address lines, so that output of a decoder will be 2 power n number of address, 2 power of n lines of the output. So that 2 power of n lines from 2 power of 0 means 1 to 2 power of n. So that it is going to have the 2 power of n number of address lines, 2 power of n address lines it can have. And this 2 power of n address lines from 0, 1, 2, 3, 4, 5, 6 up to 2 power of n address memory locations it can have. 2 power of n memory locations it can provide for the n number of address lines, and each memory location is capable of storing the data. So now this is about the RAM. It can perform the read operation and write operation. This is address lines. Number of address lines are n, and which are connected to the decoder, and the size of the decoder will be n to 2 power of n. This is n inputs, and the outputs from the decoder will be 2 power of n, and each line in the 2 power of n, each line in the 2 power of n is called as memory location. So each line in the each memory location in the entire the memory will specified by the one unique address. One unique address. For example, n is equals to 2. Address lines are 2. So that how many output lines we can have from the decoder? If it is 2, so that 2 power of 2 means it is 4. It is 4 address lines, 4 memory locations it can have, and the address of that 4 memory locations will be, first address is what? 0, 0, next address is 0, 1, next address is 1, 0, next address for the memory location is 1, 1. That means what? This, by selecting number of address lines, it is going to select the number of memory locations in the memory. And this number of address lines are going to assign the specific address, for each memory location in the total memory space. For example, if it is having only one address line, n is equals to 1. So that how many output lines we can have the decoder? That is n is equals to 1 means 2 power of n is equals to 1. 2 power of n means 2 power of 1 is equals to 2 we can have. 2 memory locations it can select, and each location will be assigned with the one specific address, that is 2 means first one is 0, second memory location is 1. Likewise, that each memory location is assigned with a specific address line. It is assigned with a specific address lines, such that the number of address lines define two things. Number of address lines defines the two things. First one is number of memory locations in the memory, and it is going to assign the specific address for each memory location. This is completed, and it is a random access memory. It can read the data and it can write the data. And so that here this is VCC, it is about plus 5 volts to on this integrated circuit, and it is ground, it is, we are going to connect all the things to the all the negative terminals to the ground. And it is a random access memory. It is capable of read and write, so that it can act as input and output. Data can be written into this memory, and data can be read from this memory. These are the bidirectional data input and data output. Whenever output enable is 0, this pins serves as output pins. That means what? The processor is reading the data, and whenever this output enabled pin is one active high, then these pins going to act as input pin so that processor will write the data into the memory. This is OE is nothing but what it is? Output enable. Based on this signal, it can read or it can write the data. And now this is nothing but it is a chip select signal. Chip select is nothing but on and off, like enable signal only. This is active, it is active low signal whenever it is so whenever the chip select signal is 0, then it is ready to perform the read and write operation. Then this is output enable and it is capable of the two functions, read and write. So that this is about random access memory. By having this knowledge, you can apply the same thing to the random access read only memory. That means what? It is going to have only this one. This pin is, we are not going to have this pin. And here these are not access the input and output. Obviously this is only read only, so that these will be access output signals only. These will access output signals only, so that in such a way you can differentiate the random access memory and the read only memory. And this is about the memory organization of random access memory. Then now here we are going with the one particular table that describes the number of memory locations and the capacity of the memory and the number of address lines. As we discussed, the number of address lines will define the number of memory locations in the memory, and it is going to assign the specific address for the each memory location. And we are going to have one particular table which describes as the number of memory locations and the capacity of the memory, total capacity of the memory locations and the range of that address lines. For example, with this example, we are going to understand the complete things about the memory organization. For example, here 12 address lines are there. Apply this example to this one. 12 address lines are there, and each register can have the capability of storing the 8-bit of data. So that 12 address lines means n is equals to what? N is equals to 12. And so that how many memory locations it can have? It can have the 2 power of 12, that is equals to 4096 memory locations have. From 1 to 4096 memory locations it can have, and each location is capable of having the 8 bits of data. So that here each location is capable of having the 8-bit of data. With this example, you can go with the complete understanding of the memory organization. Then I am going with the one particular table which describes the relation between the memory location and the capacity of the memory and with respect to the number of address lines. For example, number of address lines are 10. N is equals to what? Number of address lines are 10. N is equals to, that is 10. So the 2 power of 10 is equals to 1024, which is approximately equals to 1 kilo. 1 kilo, and this 1 kilo will be addressed from 000H to 3FFH. H stands for, it is hexadecimal number. Here we are having address lines are 10, so that it is maximum of having the memory is about 1 kilo. 1 kilo memory it can have. 1 kilo memory, and that means what? 1,24 memory locations it can have. 1024 memory locations it can have, and each location will be assigned with one specific address, and if that address starts with 000 and that 1024th location will be end with the address of 3FFH. H stands for hexadecimal number, because the 8086 microprocessor deals with the 16-bit of data, so that all the numbers it can accept in the hexadecimal. Hexadecimal is a number which can represent, which can have the base of a 16, that is from 0 to f, and so that the 8086 microprocessor can access with the hexadecimal number system. And again I am going with one more example. If the number of address lines are 11, so that 2 power of n, that means 2 power of 11 memory locations it can have, 2 power of 11 memory locations it can have, that is nothing but 2048. 2048 is equals to approximately, it is 2k, and that 2k means that is what? It is having 2048 memory location. From first location to 2048 memory locations it has, and each memory location is assigned with one unique address, and that unique address, if it starts from 00s, and the 2048th memory location will be assigned with the address line, that is 7FFH. Likewise, if you go with the 12, 2 power of 12, that is 4k, and its starting address, if it is starting address is 000H, ending address will be FFFH. But our microprocessor is having the 20 address lines. We know that it has the 20 address lines. How many address lines it has? 20 address lines. That means n is equals to 20. If n is equals to 20, how many memory locations that can have internally? That is about 2 power of 20 is equals to 10,48,576, which is equals to 1 megabyte. 1 megabyte of memory it can have. How many locations it has? 10,48,576. 10,48,576, and this 10,48,576 memory locations, the starting address will be 00000H. 0 is hexadecimal, it is replaced with 4-bit binary, and this is 0, 4-bit binary. How many zeros are there? 5 zeros are there. Each 0 can be replaced with the 4-bit binary, so that 4 into 5, it is a 20-bit address. It is a 20-bit address. Each number, each digit in the hexadecimal number is replaced with the 4-bit binary. 4 plus 4 plus 4 plus 4 plus 4, it is a 20-bit address. Starting address of 1 megabyte is what? It is all 20 zeros. And coming to here, ending address of this particular 1 megabyte of memory, it is about F. That means what? All ones, all zeros to all ones. In hexadecimal number system, that is 00000 to F, 5 Fs. Likewise, you can have the memory organization. In tomorrow's video class, I am going to discuss about some pin configurations of this memory organization. After that, we are going to study what is the necessity of address decoding actually. Here we are having address lines, we are decoding them into number of address lines, that is 2 power of n and number of address lines. Then what is the necessity of that address decoding, and such that we are going to understand how the memory can be interfaced with the 8086 microprocessor. Here you have to understand one point is that based on the number of lines of a processor, it is going to define the total capacity of a memory which can be accessed. Here 8086 microprocessor is having the 20-bit address, it is having the 20 address lines such that it defines the 2 power of 20 memory locations. 2 power of 20 memory location is nothing but it is 1 megabyte of memory, 1 megabyte of memory. And that 1 megabyte of memory can be simply accessed by the 8086 microprocessor. As we discussed in the first unit, this 1 megabyte of memory will be divided into 4 segments. And 4 segment data segment is with the 64 kilobyte, extra segment is 64 kilobytes, and code segment and the stack segment. All these 4 segments will be with the 64 kilobyte of each. 4 into 64 kilobyte, again it will be the 1 megabyte of memory. And starting location of that 1 megabyte of memory is about 0000H2, And the last memory location, that is 10,48,576, the memory location, it is about FFFFH, and in which we are going to have the 4 segment, and first segment from 00 to somewhere, and second segment next, and last segment ending address will be FFFFH. That is going to have the memory organization of 8086 microprocessor. In the tomorrow's class we are going to discuss the same. Thank you, students.